So let's review some topics for your exam. We first discussed loops. We have two main types of loops, for loops and while loops. If the number of iterations is known beforehand, then we have a count-controlled loop, which is usually best served with a for loop. Here we have an example of a for loop given. In this case, I initialized a variable named b to 99, decrease that number by 1 each time, and continue while that number, b, is greater than 0. So to inspect this loop would iterate and print the following statement when b was 99, then 98, 97, all the way through when b was 1. As soon as b became 0, this condition would become false because 0 is not greater than 0, so we would not print 0 bottles. This is just one example of a count-controlled iteration. We know the exact number of iterations, but if we have no way to determine the number of iterations before writing the loop, then we're best served using a while loop. One option is to prompt the user to stop the loop if we're getting user input. We could do something like this where we say, would you like to continue, yes or no? And as long as they continue to say yes, we continue to loop. Now this is one design that uses a Boolean, but you could also say while their answer that you read in keyboard.next does not equal n. That would work fine also. Another way to use a while loop is to use a sentinel value, meaning some kind of different value to flag the end of the loop. Like if you were reading in a bunch of exam grades, maybe tell the user up front, continue to enter exam grades, and enter a negative number when you're finished. In this example, we could design a loop so that we continued to loop while the number that was read in was greater than or equal to 0. This -1 would flag that we are no longer wanting to continue and terminate our loop. So there's all different kinds of ways to design these. However, the main difference between using a while and a for loop is that for is typically used when you have a fixed number of iterations. Some other applications of for loops, just because we tend to use them very often when looping with strings or arrays or in future other collection types. This was our first example where we have a counter set at 99, decreasing by 1 and stopping when we hit 0. In this example, I've read in a word from the keyboard and I've designed a loop that is going to go through every single index of that word. We know that with strings, indices start at 0, so I'm going to start my int at 0. I'm going to have it go up by 1 each time, so 0, 1, 2, 3, and so on, and go up to but not including that word's length. This is a good design to dynamically go through each index of a word. Very similar to this, we can also use for loops to easily iterate through arrays. So here, instead of just having a single string called word, I have an array of strings called words. Now, I have initialized this array to just hold 10 elements. We know other dynamic ways to initialize these arrays, but here I am again looping through every single element in the words array. Just like with strings, arrays have indices starting at 0. So words at index 0 would be the first word stored in that array, or the first string stored in that array. And then looping through again up to but not including the length of the array. Now one thing just to note here, because we got very comfortable looping through strings and then moved quickly into looping through arrays, the syntax is almost identical when we're doing this. However, note that length is a method in the string class, so if you're looping through the length of a single word, you want to use the parentheses to indicate you're calling a method, whereas if you're looping through an array, and again this could be an int array, a double array, or a string array, you want to use length without the parentheses. That is because length is not a method when we refer to the length of arrays. But again, just note that subtle difference there. Just like I can have a single loop, I can also have a nested loop. So combining these two ideas here, I could do something like this. I could have an array of strings, loop through every single string in that array, and then for each string in that array, loop through the different characters of that string. So I'm going to combine these last two to form a nested loop. Again, here I have a string array called words. This loop, I've changed this variable name to be j here, but it's going to go through the array named words.length, accessing every single index from 0 to 9. And then what it will do is grab each individual word. So the first time this would grab from the words array at index 0 for this first iteration and store it in a string called word. Now we're allowed to do things like this, storing this in a string, because you can see here that each individual element of this words array is a string. If this had been an int array, we could store the individual elements in a variable of type int. So again, grabbing the first word on the first iteration, storing it here in a string called word, and then having a loop here that iterates through all characters of just that word. So again, all I've done is combine these two to show you a nested loop. Now, a couple other things to consider when you're working with nested loops. One thing to really think about is that for each iteration of this outer loop, this inner loop will execute its full amount of times. So if the first word happened to be cat, this would iterate 3 times just on the first iteration of this loop. And then when you grabbed the next word, let's imagine that it was dog, this would again iterate 3 times before going back up to the following word. The inner loop is always going to execute multiple times for each outer loop, just depending on the way it's designed. Now, coming back off of nested loops to single loops, another useful implementation is the enhanced for each loop, also known as the enhanced for loop. This is very useful for iterating through arrays and other collection types that are to come. So here again, I've created an array of strings called words. Note here that I'm using the different way to initialize these. If you know all values up front, you can list them like this. We know words in this case has a size or length of 3. And here I've created my enhanced for loop that loops through the array words, pulling out individual strings one at a time, storing them in something called word. If you find that you're still confused about for each loops, please revisit that video that I made that talks about this in further detail. We've learned that arrays are reference types, and just like primitive types, can be passed in as arguments to a method or returned from a method. However, passing reference types has very different implications in our code than passing primitive types, which store the value instead of a reference. Let's look at some further examples to make sure that we understand. In the 2 examples here, I have first demonstrated method overloading by having 2 methods in the same class with the same name. However, we can tell these methods apart because the parameters are different enough. Remember, the rules with method overloading is the parameters must differ enough to tell them apart. So here I've differed by type. I've got an int array in this first method and then a single int in the second method. Parameters could also differ in number or order. That's also okay. So if we have code in both of these methods that tries to modify the parameter passed in, where a is an int and array is type int array, we need to understand the implications of how this works based on reference types and primitive types being the arguments. So first, let's imagine that we are passing in an int array named x. We know that int arrays are reference types, meaning that x would actually store a memory address or reference. This is a unique address to somewhere else in memory where the actual array contents are stored. What happens is, if x is passed into the method here, then what gets copied in is the address that x stores. So array, which is the name of our int array in this method, will now store the same address that x stores. That means that x and array both store the same address, so both point to the exact same array in memory. This should make it very clear that anything that happens to modify array inside this method has implications outside of the method. We are actually modifying the same exact array. Now, comparing that with passing in a primitive type, let's imagine that we have a primitive type here, a type int named y. Because this is a primitive type, they do not store a reference. Y actually stores in memory the value that it has in it. Here I put the number 5 in just as a sample int value, but whatever the value is stored directly under y, meaning that when y is passed into a method, the value, just like the address up here got copied, the value gets copied into A. And here it's pretty easy to determine that these are two separate copies of the number 5 in memory. They're not connected in any way. So if something happens inside this method that modifies A, maybe we add 1 to it, you can see that this number would change but does not reflect back and change the value of Y outside of the scope of this method. This is an important difference when you're working with primitive and reference types, whether you're passing them into methods or returning them from methods. So to sum this up, primitive types cannot be modified inside a method, but you should understand why. So that was this second example down here. But reference types can be modified inside a method. Just like if I were to modify array here, you can see that it modifies something that actually existed outside of the method. This is an important difference to note. Reference types are not limited to arrays, though that is our most common one we've used so far. Reference types include arrays, but also any other object. You could have a dog object, an employee object, a scanner object, and everything else that is not one of those 8 primitive types. It's also worth mentioning that new reference types that you create inside a method can also exist beyond that method. Typically, if you create something inside a method, it has a very limited scope and only exists inside that method. But because you're creating a memory address and then returning a memory address, it can then persist and exist. So in this example, I have a method named method. Again, this is totally okay to have in the same file with the last 2 because, again, my parameter list is different. This one has no parameters. But what happens inside this method is I create a new int array. So this will actually go get new memory, a brand new memory address, and then return it. You can see that I've matched the return type here to match the type that I am returning. What this looks like is when new memory is created, array goes and grabs enough space in memory to hold 1, 2, 3 and actually points to the address where that is stored. When I then return array, wherever I called this method will receive the address as an answer or a return from the method call. So if we had something that looked like this, object.method, where the method is called, it would return the address. Because the address is type int array, I could then store that in a variable of type int array, and here I've named it x. So this line of code would, again, call the method, do this work, return the address right here, and then I have written the code to store it in X. Now I'm envisioning this happening in a main method or in a separate class somewhere else. And you would have to have this object declared first. Now again, X will receive the address that is returned, meaning that it holds the exact same address that array had. We have now created a way that I can create memory inside a method. Again, this only works for reference types. Return that address and have it persist outside of this method. This will become an important topic in future classes like network applications, where you need to discuss making data persist throughout different parts of your code. So X, again, here holds that memory address pointing to the same place in memory that was earlier created. Now you might be thinking, why would this be useful to create a small array inside of here? There's plenty of applications, but probably one of the more often seen ones is that instead of passing no arguments into a method, we typically pass in our scanner object. Here I have the same example, except it accepts a scanner object named keyboard as its parameter, and we could write code inside this method that uses that scanner class to create and populate an int array. We could ask the user to enter their size, read it in using keyboard.nextInt, create a new int array of that size, and then loop through to grab however many numbers we need to grab. This works for string arrays, double arrays, any kind of arrays that we want to get. So this is a very common application here. Again, note that any memory I create inside of here, as long as I return it, I would need to have a return statement at the bottom of this method for this to function properly, would return that memory address and function as we've seen here.